This video will discuss the difference between transverse and longitudinal waves, how the speed of a wave is determined by the medium, and how to calculate the speed of a wave. Here's a transverse wave. Since it's a single disturbance, we can also call it a pulse. Propagation is the direction of energy travel in a wave. The medium is the material that the wave is traveling through. Here, the displacement of the medium is up and down. A transverse pulse is a wave in which the particles in the medium vibrate perpendicular to the propagation. If I produce a transverse wave, the propagation will be towards Mr. Peterson, but the displacement will be perpendicular to the propagation. Here we can see the transverse wave is propagating to the right, but the particle vibration is up and down, so that they are at right angles to one another. A popular physics question asks, if a wave is propagating to the left, what direction is point P moving? We know that since it's a transverse wave propagating to the left, that the particles can only be vibrating up and down. But how do we know whether it's up or whether it's down? Here's a way to visualize it so that you'll always get this question right. Look at the surfers that are waiting for the waves. When they're on the front of the wave, they're moving up. And when they're on the back of the wave, they're moving down. Since the wave is propagating to the left, the beach must be to the left. If the beach is to the left and the green dot represents a surfer, then the surfer must be on the back side of the wave. Which direction must they be moving? They must be moving down. Let's try this with the original question. The wave is again propagating to the left, so the beach is to the left. Point P, then, we can think of as a surfer, is on the front end of the wave. Which way must they be moving? They must be moving up. Longitudinal waves are different from transverse waves in that the particles vibrate parallel to the propagation.
Propagation is defined as the direction of energy travel in a wave.
When Mr. Peterson produces a longitudinal wave, the displacement of the compressions is parallel to the propagation.
Sound is a longitudinal wave, so the displacement of the particles is parallel to the propagation of the wave.
The velocity of sound is constant, in this case because the medium, which for sound is air, is not changing. The speed of a wave is determined by the medium it travels through. In this case, air is the medium, and since the temperature, pressure, and humidity remain constant, so does the speed of sound. We'll turn this speaker on and produce a low-frequency wave.
As the frequency goes up, the speed stays the same, so therefore the wavelength gets shorter. Higher and higher frequencies have shorter wavelengths because the speed is constant. When you reduce the frequency, the wavelength must get longer because the speed stays the same.
The same is true for transverse waves. As long as the medium is not changed, the speed of the wave will stay the same. but the frequency and wavelength may change inversely with one another. So what happens when we change the medium? Here we see a transverse pulse traveling slowly. When the tension in the slinky is increased, the result is an increase in wave speed. When the medium is returned to its original position, the wave speed again slows down. So let's look at a transverse wave as it moves into a new medium. As it enters the medium, the speed decreases and so does the wavelength. But notice, the frequency actually remains the same. The time it takes to complete one cycle has not changed. In medium 1, both the wave speed and wavelength are large. When the wave moves into the new medium, both the wave speed and wavelength decrease, but the frequency remains the same. A change in medium only affects the speed and wavelength. It does not affect the frequency. So if we look at the time to complete one cycle from crest back to crest, it takes 2 seconds. That's the period. When it enters the new medium, the vertical motion hasn't changed, so the time to go from crest to crest is still 2 seconds. If the periods are the same, then the wave must have the same frequency. Let's look at the velocity now. As the wave travels to the right, its velocity is high. Entering medium 2, its velocity decreases. So if we look at the wavelength is the distance from crest to crest. As it enters the new medium, it doesn't cover as much distance in the same amount of time. So the wavelength has become shorter. Now we can look at all of these factors at once in the following animation. Here we see that the velocity is large, the frequency is medium, and the wavelength is large. As it enters the new medium, the frequency remains the same, but it's the velocity and the wavelength that decrease. A change in medium only affects the speed and wavelength. It does not affect the frequency. So, how do we determine the speed of a wave? Well, we can measure the distance of the wavelength, which is measuring from crest to crest. And we can also get the period, the time it takes to complete one cycle. So the wavelength in this case is 6 meters. And since the period is 2 seconds, we can use the formula V equals d over t to calculate the speed. 6 meters is covered in 2 seconds, so the velocity is 3 meters per second. Box that puppy up, and we're done. So here's an interesting derivation. If we start with the formula V equals d over t, we know that the distance covered is a wavelength, and the time it takes to cover that distance is called the period. So now we have V equals lambda over t. Now, if we recall that t equals 1 over f, we can substitute in 1 over f for t, the period. That will give us V equals lambda over 1 over f. Multiplying through by f over f, we can cross them out, and we're left with V equals f lambda, the formula for the speed of a wave. This is so exciting, let's double box it. Oh yeah. So we've seen that we can use V equals d over t to find the speed of the wave. But what if we use the period, 2 seconds, to figure out the frequency? Then we can use our new formula, V equals F lambda, put in the frequency, and add in the wavelength, and we can see that we get the same exact answer, 3 meters per second. We should box this up because that's pretty exciting. But this is so exciting, I think we should also include a unicorn. And let's go a bit further and add a rainbow. Yeah, that was a pretty exciting problem. Okay, so this is looking down the center of the slinky, and this is just really cool looking. So here's a transverse pulse. And here's a longitudinal pulse.
So something higher than this?
Not a whole lot more. What are you at?
1.1. So that must, is that 1,000?
But are you on 1,000? Yeah, 1K.
Yeah. Alright, so that's 100 hertz then.